And hello everyone. My name is Fikriah Hani Omar Bakhri. I am from Universiti Teknologi Perak. Today, I will be sharing our research on architectural design strategies for integrating food waste to energy system into adaptive reuse project in Georgetown, Penang. The study explores how food waste generated from buildings can actually become a valuable energy resource, particularly in dense heritage city. So first, let me give a quick review for the study. To begin with, this summarizes the research using the 5W1H framework. Firstly, what is the research is about? The study focuses on developing architectural design strategies to integrate food waste to energy systems, specifically wet anaerobic digestion into adaptive reuse building. The next one is, where is the research conducted? The study focused on Georgetown, Penang, which is an UNESCO World Heritage City characterized by dense urban fabrics and many adaptive reuse buildings with food-related function. Then, why is this research important? Currently, most urban waste is still sent to landfill, which opportunities for on-site energy recovery within building remain underexplored. In terms of how the research was conducted, the research applied a systematic literature review together with precedent study analysis. In terms of benefit, the outcome are relevant to architects, adaptive use developer, and urban waste management stakeholder. Finally, the output of the research is a set of architectural design strategies for integrating decentralized wet anaerobic digestion system into a heritage adaptive use project. Now that we understand overall scope of the research, let's first look at the broader urban food waste challenges. Cities today are producing more and more food waste, mainly because of rapid urbanization and increasing food consumption. In Malaysia, most of this waste is still managed through centralized collection system and landfill disposal. But the thing is, food waste actually contain a lot of organic material that can be converted into renewable energy. So instead of seeing food as something to dispose of, we can start thinking of it as a recoverable resource within a circular urban system. So with that in mind, the next question is, why focus on Georgetown? There are several reasons why Georgetown was selected for this research. The first one is it is as a UNESCO World Heritage Site with a dense historic urban environment. Second, the city has a strong food culture with many restaurant, cafe and food-related business. A lot of heritage buildings here are adaptively reused for this function, which means they generate a continuous stream of food waste. However, this waste is usually collected and transported off-site. So this creates interesting opportunity to explore building scale waste to energy system within this adaptive use project. Despite this potential, there is still an important gap in current research. On the left side, we can see current research focus. Most existing studies concentrate on technical performance, anaerobic digestion, environmental impact of food treatment, and urban waste management policies. These studies generally treat food waste to energy system primarily as engineering infrastructure. On the right side, we can see what is missing in the literature. There is limited research addressing spatial integration at the building scales, architectural planning strategies, and integration within adaptive reuse and heritage building. So, we identify the research gap. This leads to the research need, which is to develop design-oriented strategies that translate technical system requirement into architectural solution. So, based on this gap, we develop the following research aim and objective. The aim of this research is to develop architecture design strategies for integrating food waste system, specifically wet anaerobic digestion, into adaptive reuse project in Georgetown. To achieve this aim, three research objectives were established. The first objective is to identify current urban food waste management and food waste to energy approaches with a focus on the suitability of wet AD for building scale application. The second objective is to evaluate selected precedent projects to understand the spatial and operational requirement of integrating wet AD system within adaptive reuse building. And the third objective is to propose architecture design strategies for integrating food waste to energy system into adaptive reuse project in Georgetown, Penang. To achieve this objective, the study adopt the following research methodology. Study use qualitative design-oriented approach. There are two main methods. The first one is systematic literature review, which looks at research on urban food waste management and wet anaerobic digestion technologies. The second method is precedent study analysis, where we examine real-world example of decentralized AD system to understand how they spatially integrated. Let's start with the literature review process first. For literature review, we use Scopus and Science Direct database because they cover a wide range of research in environmental science, sustainability, and built environment. We apply a structured screening process including title and abstract review, duplicate removal, and relevant filtering. After the process, there are 26 studies were selected for detailed analysis. In addition to literature review, we also analyze several precedent projects. 3 precedent projects were selected based on several criteria, such as their operational in dense urban environment and their use of wet anaerobic digestion system. These cases include the SEAB Flexibooster system in the UK, the East Coast Lagoon Food Village system in Singapore, and the Camberley Street Micro AD system in London. So now let's move on to the key finding. Focus on urban food waste management system. From 15 papers, several themes have been emerged, including centralized waste governance and landfill dependency. The second one is policy, governance, and implementation gaps. The third one is environmental and emission performance. The fourth one is circular economy and resource valorization. The fifth one is decentralization and multi-scalar urban system. And the last one is spatial and building scale relevant. Overall, this finding revealed that a spatial disconnection between buildings that generate food waste and the system that treat it. Next, we go for the second stage of SLR, which focus more on specifically anaerobic digestion technologies. 11 papers have been studied, and there's a 5 themes that have been come up from all the study. The first one is wet eddy sustainability for high moisture food waste. Second, decentralized and building scale deployment. The third one is modular and compact configuration. The fourth is on-site energy use and urban resilience. The fifth one is spatial and planning consideration. To complement this finding, we also look at the real-world precedent project. One, SEAB Flexible with the UK, East Coast Lagoon Food Village Singapore, and the last one is Camberley Street Micro AD. There are several variables studied based on these 3 precedent study, which is system scale, site contact, zoning and spatial placement, process configuration, integration with existing function, modularity and flexibility, physical footprint, and the last one is energy output. Let's go more detail on the system diagram. Starting with the first example, SEAB Flexibooster system. In this case, all system components are integrated within a singular modular container unit. This demonstrates that modular anaerobic digestion system can be placed within service zone, scale accordingly to the amount of food waste generated. Importantly, the modular configuration also allows reversible installation, which is particularly suitable for heritage building where permanent structural alteration must be avoided. Moving for the second example, which is the East Coast Lagoon Food Village in Singapore. Here we can see that wet eddy system arranged in 2 separate containers. One container houses the pre-treatment and digestion process, while the second container manages biogas handling and digested storage. This example shows that eddy system can be operated within active food environments, and that system component may be organized in either co-located or distributed configuration depending on spatial condition. Finally, for the Camberley Street Micro AD system in London, it is demonstrate how micro-scale anaerobic digestion system can be arranged in a very compact layout. The diagram illustrates both the process flow and the compact spatial arrangement of the facility, showing that AD system can be integrated even in small urban sites with limited space. So, when we combine the finding from the literature review just now and this precedent study, several key spatial principles begin to emerge. Let's go to look all the key principles. Left side, we can see that spatial principle derived from literature review and precedent study. First, wet AD systems are suitable for high moisture urban food waste, confirm that their technical feasibility. Second, modular and containerized system enable installation within dense urban environment. The third one is effective system follow a linear waste flow, meaning there is a clear sequence from waste input to digestion to energy output. The fourth one is successful integration required service zoning, ensuring separation between public spaces and operational areas. And the last one is system placement must be aligned with the existing building function and service infrastructure. From this finding, we conclude that decentralized food waste to energy integration depends largely on spatial plannings rather than just only technical capability alone. On the right side, we look at the architecture mediation within adaptive use context. Adaptive reuse building often have fixed structure grids, limited service core, restricted access, and convention-sensitive heritage fabric. Additional system requirements include enclosed ventilation, safety zoning, and integration with mechanical system. However, there are also present opportunities, including underutilized back-of-house spaces, close proximity between waste generation and treatment. Therefore, architects play a crucial role as system integrator, translating biological process into spatial design strategies such as configuration planning, functional zoning, service routing, visibility control, and reversible installation. Based on this insight, the study proposed several architecture design strategies. Here are the 6 architecture design strategies that were identified. The first one is input lead system sizing, where system capacity determined by actual food waste generation. It prevents oversizing and reduce spatial demand. The second one is modular and scalable configuration. Prefabricated and containerized IT system help to expand or reduce accordingly to the waste input. The third one is site responsive configuration. System layout adapted to the existing building condition, which is divided into 2, co-located or distributed configuration. It is depending on the available space. The fourth one is functional zoning and service separation, which is waste processing located in the back of our service. Clear separation between public and operational area. The fifth one is reversible integration in heritage contact. Use non-invisible installation method. Avoid permanent modification of heritage structure. The sixth one is, which is the last one, direct energy application. Biogas used for cooking, heating, or electricity generated within the buildings. Finally, I will summarize the key contribution of this research. In conclusion, this research demonstrates that decentralized food waste to energy system can be integrated into adaptive reuse building through architecture planning and spatial design strategies. The study highlights that the role of architect as a system integrator in circular urban infrastructure. Ultimately, adaptive reuse building can become active contributor to circular urban metabolism rather than simply producing waste. That's all from me. Thank you.